All right, class, we're going to briefly talk about probability distributions. And so this gives you some stuff to work with. So making a probability distribution. So probability distribution represents probabilities of all events. And we often need a table or figure to help us figure out what that would be. So we want to list them, something to list all the possible outcomes. That's the big piece there. And then after we do that, we want to identify the outcomes that represent the same event and determine the probability for each one of those. Then we put that into a table. So we make a table listing each event and probability. This is a probability distribution. The first piece, this first table, not a probability distribution, just something to help us list all the outcomes. This, where we've identified the outcomes that represent the same event and determine the probability of each event, that is our probability distribution. And that is its own table. An example is, consider that we're going to roll 2 6-sided dice, and we're really concerned with the sum of the 6-sided dice. We're not concerned with a particular result, we're concerned with the sum. This means 2 and 2 is 4, but 1 and 3 is 4, or 3 and 1 is 4. So it could be any of them. So this is why we often create a table, just to keep everything together and to keep things organized. So the possible outcomes, this first piece up top here, is just our guide, right? This is just to help us. Oops, didn't mean to do that. Let's go back. This is just to help us. This down here, this is our probability distribution for the sum of 2 dice. If you'll look, 2 only happens once, right? So there's 1 out of 36. 12 only happens once, 1 out of 36. 3 happens twice, either 2 plus 1 or 1 plus 2. Just like 11 happens twice, 6 plus 5 or 5 plus 6. So 2 is 1 out of 36 probability chance or likelihood. 3 is 2 out of 36. 4 is 3 out of 36. 5 is 4 out of 36, etc. We've listed them all up. I left them with a common denominator instead of simplifying because it would make it easier to add these up. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 is 36, which would be 1. 36 over 36 would be 1 or 100%. The questions that could be asked might be, what's the probability of getting a value greater, 8 or greater? In which case we have 8 highlighted, and I could add all these up because I've made this table. But more importantly, I can go down here and say, well, that's 5 out of 36 and 4 out of 36 and 3 out of 36 and 2 out of 36 and 1 out of 36. And I can add them all up and say 15 out of 36. 5 plus 4 plus 3 plus 2 plus 1 is 15 over 36. And whatever that comes out to be or simplifies to be as a decimal is the percentage, the likelihood, percent likelihood that I'm going to get an 8 or greater on 2 6-sided dice. Sometimes it's also nice to look at trees. I want to point out that the reason 7 is considered a lucky number in many gambling games is simply because there are more probable outcomes, probable ways to roll a 7 than any other number. So that's the reason 7 is considered a favored number. It's easier to get with 2 dice, 6 out of 36. None of the other numbers are that high. Just a little interesting bit of tidbit. Sometimes we will just want to count outcomes. So here I have 2 coins and I'm going to flip them, and they're fair coins. So if I flip coin 1, I could get heads or tails. For each one of these, when I flip the second coin, I can get a head or a tail or a head or a tail. So this gives my total outcomes with 2 coins as 4. There's 4 possible outcomes: heads, 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 tails, tails, heads, or tails, tails. Suppose we toss 2 coins and want to count that total number of outcomes. 1 on the first, the second one also has 2, so we end up with 8. So 2 outcomes for the first coin can occur with either of the 2 outcomes for the second coin. So we end up with 8. We can think of this as 2 or 4. So we can think of this as 2 times 2. And that's really what's happening. There's 2 outcomes for the first one, 2 outcomes for the second one. Well, this means what happens if I added a third coin? Well, that each one of these, this head could have heads or tails, this tail could have heads or tails, this head could have heads or tails, this tail could have heads or tails. So we end up with 2 times 2 times 2. So if we were looking at 3 coins, we would have 8 possible outcomes. And I've listed the outcomes below, and I also have a tree diagram to show you. And there's the tree diagram. Now, I should say that the more you get, this becomes harder and harder to do. You wouldn't want to do this with something like a deck of cards, 52 possible. The French deck or the deck that we use here in America is the French deck, and we have 52 cards in there. That would be a huge list and probably be difficult to draw. But if you had to flip a coin and roll a dice, you could probably do that. We may want to talk about different ways that we could get a entree and a special at a restaurant where it's made up of an entree, a side, and a dessert or something like that. And as long as there wasn't a ton of possibilities, you could do that with a tree diagram. Let's take a look at an example. So a class is choosing a president, vice president, and a treasurer. 2 students are running for president. 2 students are running for vice president. And there are 3 students running for treasurer. This question says, create a tree diagram that shows the possible outcomes and then use the diagram to answer the following questions. So first we need a tree diagram. We'll choose the president first, then the vice president, and then the treasurers. So you could have Linda or Maria chosen, and then you could have John or Bob, and then you could have Amanda, Deborah, or Jessica. So here are all the possible outcomes, okay? And we have them listed here. For each case, Linda and Maria, you could have John or Bob, and John or Bob. And then for each one of those cases, you could have Amanda, Deborah, or Jessica. Amanda, Deborah, or Jessica, doesn't matter. So the question is, how many outcomes are there? In this case, we're only counting the ends, and there are 12, 2 for the first choice, 2 for the second choice, 2 times 2 is 4, 3 for the third choice, so times 3, so that's 4 times 3 is 12. Or you could count all these, either way. In both cases, you should get 12. And then it asks, how many outcomes have Amanda or Jessica being chosen? So Amanda and Jessica are both running for treasurer. So we really just have to go down the list and say, well, there's Amanda, there's a Jessica. There's an Amanda, there's a Jessica. There's an Amanda, there's a Jessica. So there should be 8 possible ways. The other option is because there's only 3 people, you could say, well, how many times does Deborah show up? Deborah shows up 4 times, so 12 minus 4 would be 8. But in this case, we can just count them, and there's 8. Because we're counting ors, so Amanda or Jessica, either one is okay. Now, how many outcomes have both Linda and Bob? So now we're really looking at Linda, Bob, and then these choices. We're not looking at any of these other choices. We're just Linda, Bob. There's only 3 of them. And it's these 3. It's the 3 that have Linda, Bob, and then either Amanda, Deborah, or Jessica. So there's only 3 outcomes. Now this is asking for the number of outcomes. It could very well ask for what's the percent that Linda and Bob will be chosen. And then you could go, well, 3 out of 12 is the percent. Next, we have the try. I wanted to just throw up there. One spinner has 2 sections. They are marked A and B. Another spinner has 3 sections. They're marked 1, 2, and 3. And the third spinner has 2 sections. One is green, one is pink. The 3 spinners are spun. The tree diagram shows the possible outcomes. And here it is. So you're given this, and then you have to answer these questions. Leave that up, let you guys give that a go. And that's really all I have. We'll continue the conversation in the next class. Have a wonderful day.